Okay, YouTube, in this video I'm going to cover everything about inverse functions, including their definition, how we verify them graphically, talking about whether or not inverses are themselves functions, and last but not least, how you actually find them algebraically. So let's go ahead and begin with what we mean by inverse functions. And I'm going to actually write this as like an undoer function. Basically, when you hear inverse, we mean a function that is going to do the exact opposite of an initial function, okay? So we do write inverse functions like this. We say f inverse of x. We use this f of -1 here, and we don't want to confuse that with exponents, but basically we would write that to denote the inverse of some function f. And so let's talk about what we mean by what an inverse's job is here. So let's consider that a function is basically a mapping of some x values in the domain of f into a rule and mapping them onto some range values, f of x over here. So basically it maps x values to y values. That would be our rule f. What we want to do is find some new rule, and we're going to refer to this as f inverse, that does the exact opposite. It would, if you were to take these y values and stick it into f inverse, what it's going to do is it's going to take them and send them back to the initial x value. So essentially, if we were to say hypothetically, let's consider a relation here, f, where we had some input values. We'll go with 1, 2, 3, and we'll double them. We'll say that's my rule here, 2, 3, 6. And what f does is it takes all these here and it doubles them and maps them over to here underneath this rule here. So we have x over to f of x values. And so we would get some initial 1, 2, 2, this would be a 4 by the way, 2, 4, and we have 3, 6. This would be our rule f. The inverse function, by definition, f inverse, would do this. It would take all of these outputs, and when you stick them into f inverse, right this way, okay, let's do a different color here. Let's go with like a red. F inverse, what its job is it's going to take all the initial outputs, and when we stick them into f inverse, send it back to the initial input. So basically, this is what's happening right here. It would take 2 and send it back to 1. Take 4 and send it back to 2. Take 6 and send it back to 3. So if we were to define this function here, it would look like this. I plug 2 into it, and I actually get sent back to 1. Or if I plug 4 into it, I would get sent back to 2. Or if I plug 6 into it, I would get sent back to 3. Okay. So the idea that I want to start with is essentially this. The domain of f is all these x values over here, and the range would be all these f of x values. Well, when you switch this relationship around, okay, what we're doing is we're taking the original range values of f and plugging them into f inverse. So what this means is these original range values become the domain of f inverse, since we're plugging those into f inverse. And the outputs here, which were the original domain values, actually become the range of f inverse because we are mapping onto those values here. So what I essentially want everybody to notice is this. Inverse functions have domains and range that switch, okay? The domain and range just switch on these inverse relations here. So let's take a look at the definition of an inverse function here formally, but we say that two functions f and g, let's let them be inverses of one another. And if that is true, then what's really going to happen is we're going to be able to satisfy both of these conditions. The first one being that if I were to plug g of x into f of x, which f of x is g of x's inverse, I could write g inverse, we would get sent back to an initial input value or an x value. So basically this is true for all x in the domain of g. Likewise, if we were to take all the outputs for f of x and stick it into its inverse function g of x, then all the outputs would be sent back to an initial x value or an initial input value, okay? But under these conditions, we would say that these two functions are inverses of one another, all right? Essentially, what we're saying here is this. Instead of using f of x and g of x, let's look at it this way. If the function g is denoted by f inverse, okay, so we say there is an f of x and an f inverse of x, then what we're going to say is this. I'm going to look at this one on the right here, but we say if f inverse is the undoer function, what it's bound to do is this. Take all the outputs of f, take all the y values of f, and when we stick those y values of f, like these ones we had over here, these y values, and we stick them into f inverse, what happens is they get sent back to the initial x values that we had started with. Likewise, if we take all the output values for the inverse function and stick it into the original function, which is its inverse, we get sent back to the initial x values here. Okay, so let's take a look at what this would mean or imply graphically. Okay, so inverse functions graphically. The first thing I want to read here is basically this. It says switch the coordinates of the points in f of x to find f inverse of x. And when I say switch the coordinates of the points, what we're basically going to write is this. If xy is a point on the function f, then it is true that the point yx is a point on f inverse. Remember that all we really did looking at these points over here is if we had an initial xy, if you switch those around, that is, if you plug the y value into the inverse, it gets sent back to the original x value, the domains and ranges switch. That's what's happening. So when I say switch the coordinates of the points in f of x to find f inverse of x, basically take all the original points xy and make them yx. So taking a look at this relationship that I have here, for instance, this is y equals x squared, or I should say f of x equals x squared. What we'll do is we'll take some points here that are noteworthy, like 0, 0, and 1, 1. We'll actually grab 2, 4. Well, how about 3, 9? 3 squared is 9. And also these negative 1, 1, negative 2, positive 4, negative 3, positive 9. And we'll switch the domain and range around. So if this is the point 0, 0, then when I switch those around, it's still 0, 0. If I take 1, 1 and I switch those x and y values around, I still get 1, 1. But here's where it starts to get interesting. Instead of going right 2 up 4, if I said plugging 4 into the inverse function, it actually gets sent to 2, then this would become on the inverse function, 4 goes to 2. And on the inverse function, if I were to take the output 9 up here, okay, 9 was paired with the input 3, plug 9 into the inverse function, it's actually going to map onto 3. So all I'm really doing is taking all the x and y values and I am switching them around, switch the domain and range, okay? Likewise, negative 1, 1 would now be at, instead of negative 1, positive 1, we'd be at positive 1, negative 1. Also this, we would say, instead of being at negative 2, positive 4, we'd be at positive 4, negative 2. Instead of negative 3, positive 9, we'd be at positive 9, negative 3. So we could say that this graph that we see right here, this would be f inverse of x. And I'm not so concerned with the rule as much as I am concerned with the points just switch. So a couple of notable things here. First of all, the domain of the original function up here, this is f, okay? The domain of that function was negative infinity, or is negative infinity to infinity. It goes left and right forever and ever, whereas the range, I notice, is all at y values greater than or equal to 0. So we say starting at 0 and going up to infinity. If now we were to list for f inverse its domain and range, notice this. The domain of this function is actually only x values greater than or equal to 0. So we'd say on the interval from 0 including 0 out to infinity, and then the range here would be, well, all y values. So we'd say the interval from negative infinity up to positive infinity here. So you'll notice that the domains and range simply switch when you switch your x and y values around. And last but not least, to verify that two functions are actually inverses of one another, all we need to notice is that they are reflected about the line y equals x. So I will sketch in that line. It is just our parent linear function here that has a slope of 1 and a y-intercept of 0. But all inverse functions, as a result of the graphical properties here, switching domain and range, will be reflected over this line. Okay. So let's talk about horizontal line test. The horizontal line test, what it does is essentially this. We'll type this in here. It tells whether the inverse is a function. That's all. Okay. So let's remember something here. When we want to find out whether something's a function or not, just whether it is a function or not, usually what we do is we use this thing called a vertical line test. And the vertical line test is just checking to see if the function is one-to-one. That is, each value of the dependent variable, or the y variable, corresponds to only one value in the independent variable, or the x variable. So basically, every x value is going to go to one and only one y value. And we can see that with the example that I'm using here, that this parabola here, this blue parabola, it would pass the vertical line test because no matter where I draw a vertical line, it'll only ever hit my graph once. What I want everybody to notice, though, is look at its inverse function. If I said, well, now looking at the inverse function, is the inverse function, is it a function? And I would say, well, no, because when I draw a vertical line here, I had an x value here that went to two different outputs, or two different y values. So instead of having to do a vertical line test after finding the inverse, what we do is we say, well, because I know that these graphs will just be reflected over the line y equals x anyways, if my original graph, if it were to fail what we call a horizontal line test, boom, right here, that fails the horizontal line test. Then I know that when I graph its inverse relation, I will know that it'll fail the vertical line test at that point. So the horizontal line test is kind of like foreshadowing. It says if it doesn't pass the horizontal line test now, then its function actually will not pass a vertical line test. So that's how it's telling us whether or not the inverse is a function, okay? So for this last two examples here, we're going to take a look at how would you find the inverse of a function algebraically, which really is the most important thing in this entire video if you ask me. So I've got some steps written out here. The first one is this. Let's change all f of x to y, so we just have x's and y's. And then what we're going to do is we're going to take all y values, make them x values, and take all x values and make them y values. This, you guys, is essentially just saying that the domains and range switch here. So if I know this happens with all the points, then what we're going to do is we're going to take the rule in general, and we're going to switch x and y. And the neat thing about this is that is the inverse. That is already the inverse because you switched x and y. Everything after this is just common practice. So that is, we like to write y as a function of x. We're going to isolate y, and then we're also going to replace y with f inverse of x at that point to denote that this is actually the inverse function, and we're going to verify this, and we can verify this both graphically as well as algebraically, which we'll do both here. So let's take a look at f of x. We want to go find f inverse of x. So the first thing I'm going to do is say, well, f of x is the same as y, and what I want to do to find the inverse is just this. I'm going to take that x and I'm going to make it a y. Sorry, make the y an x, and I'm going to take this x over here on the right side and I'm going to make it a y. So I end up with this function right here. And essentially what I can tell you already is this is the inverse. This is it. Right now, this is the inverse. So the only thing I'm really wanting us to do is to solve for y, which means I'm going to multiply both sides by 2 here. So we get this. We get 2x. It follows that 2x is equal to 5 minus 3y. And then to get y by itself now, we'll go ahead and displace this 5. So we get 2x minus 5 is equal to negative 3y. And then dividing both quantities by negative 3. Okay, what we're going to end up with here is this. I'm going to say y equals now positive 2x divided by a negative 3 actually is, let's do this. Let's take this negative here and we'll put it on the top. Okay, and so what we end up with is actually negative 2x plus 5 over a positive 3, and this right here we're going to say that this is f inverse of x. Okay, so we found our inverse function. The last thing we need to do is actually verify this. So what we're going to do is actually going back, looking at the definition of inverse functions in the first place is this. I'm going to point out the fact that if these are inverse functions, then when you find their compositions, when you plug one into the other, you should just go back to x in general. You should get x as an expression. So what we're going to do here is we're going to make a substitution, and I'm just going to choose to check this as f inverse of f of x. Essentially what we're doing is taking every single y value for the initial relation and plugging it into its inverse and saying, did I get back to x in general? So because I'm plugging into f inverse of x, and my f inverse of x is this negative 2x plus 5 over 3 thing, I'm going to say I get negative 2 input plus 5, and this is over 3, and we're going to go plug in f of x. So I get 5 minus 3 of x all over 2. And we're going to say, well, first thing I notice happens is these cancel out. This becomes a 1. This becomes a negative 1. So now I'm left with this. Negative 1 times 5 minus 3x plus 5 all over 3. And distributing this negative here, that would make this a negative and this a positive. I notice that my 5's cancel out. And now I'm left with just 3x over 3, which gives us just x. So the fact that we ended up with just x means that these must be inverses of one another, okay? So now our initial function, 5 minus 3x over 2, let's take a look at it. So we have 5 minus 3x, and I want to quantify that here. So 5 minus 3x all over 2. We have this function here. When we graph its inverse, remember its inverse we are able to find as negative 2x plus 5 over 3. So if I type this in, negative 2x plus 5 divided by 3, I can notice some things here, like for instance, this is the point 0, 1.667. If I go over to this graph and I try to get really close to 1.667, we'll do that. It's at 0. Okay, so I notice that these are actually reflected over the line y equals x. I can see that here. Okay, so now let's take a look at this last example. Thanks for being patient with me here, but you'll want to see this one because we use this one a lot. Let's say I have some function here that is a rational function that looks like this. First thing again, when I want to find the inverse is this. We'll replace this with y, and then we're going to switch all our x's and y's around. So I get x equals y minus 3 over y plus 2. So here's where this tricky part comes in. The fact that I have y's in both places and I want to solve for y means that we're going to have to use some algebraic sleight of hand. So what I mean is we're going to multiply both sides by y plus 2. This is the technique. And what we get is this. We get x y plus 2x. I just went ahead and distributed this here. And on the right side, we're left with y minus 3. So our job is to get y by itself, which means we're going to have to round up all the y's on one side. So if I subtract y from both sides, and actually I'm going to bring this 2x over here. I'm going to subtract 2x from both sides, minus 2x minus 2x. What we get is this. We get xy minus y on the left. And on the right side, I'm going to have a negative 2x now, since I displaced it over here on the right, minus 3. So the trick with getting y by itself here is that we're going to factor the y out. And when I factor this out, I get y times x minus 1. And this is equal to 2x minus 3, and the 2 is negative there. And then we're going to divide both sides by x minus 1. And you can see that this is effective in isolating the y. So what we discover essentially is this. We get y is equal to negative 2x minus 3, that over x minus 1. And again, what we want to do at this point is we want to say, well, that y right there, that's really f inverse of x. So here's our inverse function. So to verify this, we could do this graphically and algebraically.